Hi, welcome to Social Research Insights. My name is Kamaksha Musnur. I'm Principal Consultant at Social Research Insights. Social Research Insights is not a business organization, it's just a freelance training outfit. We're just a couple of individuals who are working on freelance style. We provide training on data science, analytics, and IoT. We have a lot of content online, and all the content is free. However, we have a request. Consider calling us for staff development or faculty development programs in your respective organizations or institutes. This is in fact one of my demonstrations which belongs to a series of presentations and they're related to data analytics through Python. In my previous videos I've shown how to understand the T distribution with the help of degrees of freedom, and also shared a particular part of the area under T curve. In this video I'm going to show you how to write a couple of functions to test the normality of underlying data. So as a matter of convention, whenever we have some sample data, before we go for the bivariate or multivariate analysis, we check very rarely we check some of the conditions like the property of normality, etc., something like that. And this normal property or the normality test is one of the prerequisites, especially when we are going for some bivariate regression or maybe multivariate regression, something like that. In this video cast I'm going to show you how to write a couple of functions to deal with a normality test. I chose Jarque-Bera Normality Test because it's very simple and easy to calculate. At the same time, there are the pros and cons. Like, there are also disadvantages with this normality test. In case if you want to know something about the Jarque-Bera Normality Test, you have a beautiful Wikipedia page on Jarque-Bera test, something like that. We have to compute Jarque-Bera statistic, JB statistic, that depends on two important descriptive statistics of the underlying data. That is one of the statistics which we need to compute the Jarque-Bera statistic is the skewness, the other one is the kurtosis. And this is the expression for the skewness, I should say the mathematical expression for the skewness, and this is mathematical expression for the kurtosis. So we need to compare the skewness and kurtosis, and later we need to calculate a composite statistic based on these two important requirements or inputs. It is very easy to say, but to do the same is not that easy as I am talking to you. We need to write a couple of other statistics. For instance, if you see this skewness, you have mean inside, and when we deduct this mean from the actual observation and raise it to 2, that is actually the variance. Okay, so we need mean, and we can do all these calculations using that only one descriptive measure. The representative of the is a location. So let's go ahead, and I open the new file. This is a script file. I'm going to write all the functions required to compute the Jarque-Bera test. The first one is going to be the mean. Now we finished the mean, and we need to go ahead and write the functions for skewness and kurtosis. For that we need to observe the formula. Anyway, we are not going to make use of this. I have a rather simple expression for the Jarque-Bera statistic, but we'll be following this two methods for skewness and kurtosis. I think these are the very simple methods we have right now. For this, what happens, I am going to create the numerator, denominator separately. In denominator we have the two different terms, like say first we need to find the sum of the differences squared. We have to find the difference between the actual observations and mean. We need to raise it to 2 and then sum of them, and after we multiply with 1 by n, then we raise that entire product to 3 by 2. So this is what first numerator. In denominator we have denominator part 1 and part 2. So remember this. Now we return the value by simply finding the numerator to that of denominator. Now select entire, then compile. Yes, of course it seems to be my mean range 1. I think we got a 0. Float division by 0. Return numerator by denominator. Okay, let's go back and see. I checked the numerator, and the numerator obviously will turn down to be 0, so there is nothing wrong, but the denominator can't be 0. So the denominator has some valid, because here denom 1 has some valid value, but it cannot be. So we need to keep some float here. That we can solve with the help of statement float. So I think now it is okay. Yes, correct. Skewness, let's say x is equal to range 1,10, and skewness, 0. So it can be 0, so which means it is obviously it is normal, right? And then let's go for the kurtosis. Same strategy will follow for the kurtosis, but this time I'll raise it to 4, and then we'll multiply with 1 by n. Then the total sum of the square differences will be raised to 2. I'll just copy the statements in the previous, because all of them are identical. We need not write once again all of them. Only change is that I should make here 4, then I will come here, and the square is square common, and here we need to change, instead of 3 by 2 I just have to make 2. I think that will do the trick. I mean, that is the trick we need to do. Select entire module, and then now go for the cut to x. I'll simulate some data. Kurtosis x. I think this has some skewness. This is 0, so it roughly normally distributed. So let's go ahead and do the, I'm not going to make use of this expression for Jarque-Bera test statistic. We have the other expression, and you can just Google the other expression for the JB test statistic. The static goes like this. So let me put you that. It's very simple. Like even in this expression, we can even follow this same expression, but this expression is little complicated because we have k here. It is not 1 minus k plus 1 by something like that. We can just simply take, I think we can, we have another example, that is the Jarque-Bera test statistic can be computed like by multiplying with n, which means the length of x, skewness squared by 6 plus kurtosis squared by 24. That's it. So this is what is the Jarque test statistic for the Jarque-Bera, and we are going to do the same thing in Python. I call it as JB test, and it is univariate normality test. It's very simple. We just have to make an expression. The skewness is going to be skewness, since we have this function in our module, skewness x, and kurtosis is going to be kurtosis let me see, yeah, x. Then we have JB statistic, JBS, and that is going to be the len of x multiplied s square divided by 6 and close plus open parenthesis k square divided by 24 and close parenthesis close parenthesis. That's return JBS. Now we need a probability p-value to take the inference or decision. For that we need to go back and see. We'll go back to the Jarque-Bera. Somewhere you'll find that the sample the Jarque-Bera is approximately equal to the chi-square distribution. I mean, if the sample size is marginally large, then the JB will asymptotically chi-squared will be distributed as a chi-square distribution with 2 degrees of freedom. We need to figure out. We need to find a way to compute the chi-square test probability. For that, it is a bit complicated. But it's not that complicated. But let me tell you one important procedure. Suppose we want to find the p-value for a normal distribution. Let's say we know that the p-value for the p-value for a normal distribution for 1.96 is 95.95, right? So let us see that. For that we need a particular package called stats from SciPy, package called SciPy, and in this SciPy we have a module called the stats. We need that particular module from this package. Import stats. Now what I do, I'll try to show you how to find the p-value for the required quantile of the normal distribution. Suppose I want to find the probability value for a normal distribution where the Z value is equal to 1.96, because we know this value. That is why it is easy for us to check stats norm PDF and 1.96. then I'll try to put 0 1, which means I want the probability value from the exact normal distribution. Now you see this is 0.05, but we know that it should be 95, right? For that, what we need to do, we have to take the difference from 1. Now you'll get the 95% roughly, not exactly. So the same strategy we'll try to follow, and once we find the Jarque-Bera test statistic, JBS, then we need to find a way to, since we know that it is a chi-square distribution, I mean this test statistic roughly follows the chi-square distribution at 2 degrees of freedom, then perhaps we can try to find the probability this way. We have chi-square PDF module from this stats package, stats chi-square PDF. Then we need to give some value. Let's say I'll just try to give some test value and 2 degrees of freedom. Then you will get some value for the p-value. Just like the way we find the p-value for the normal distribution, we'll try to find the p-value for the chi-square distribution by using the function PDF. Okay, and come back, return. We want to return that p-value 1 minus stats chi-square PDF JBS and for 2 degrees of freedom. That's all. And since we are using the stats package, so we need to add that particular statement here, top of the here, from stats import, from SciPy import stats. That's all over. Now let us run this module. Yeah, there are no errors. Now what I do, I'll try to simulate some data set just as we did earlier. Range 1, 10, some 9 values, 1 to 9 values. Now let me test all my functions over. My main x My I think my standard deviation is not there. Skewness x, kurtosis x. Okay, it's fine. Now let us go for Jarque-Bera test x. Yeah, so we got the p-value 0.72, which means if the p-value close to 1, then we fail to reject the null hypothesis. In this case, the null hypothesis is going to be that the underlying distribution is normally distributed. Now we'll also check in another way. I can simulate some normal distribution by using a package called numpy. I first import the numpy. Import numpy as np, and in numpy we have a normal distribution, random normal distribution, normal variate, variate with I request 100 data points from the normal distribution, and this time I try to save this as y, and then we'll test this distribution whether it is normally distributed or not, because we know that it is normal distribution. Yeah, it is 9999999. So our test statistic is correct, and our probability, our strategy to find the probability from this particular strategy is correct, because since we tested knowingly, we have taken the data from the normal distribution, and we tested our function, and it is passed the test. The value is very close to 1, which means that our method or our procedure for testing normality, univariate normality, is correct. Now I'm going to show you a particular way of using this descriptive file as in the form of a module. The module is going to be, I am going to save this file. I think I already have this file somewhere in directory work Python. So what happens is that I'll close everything, and I will also close this. I need not close this script file. I'll close the editor and go back to the directory in my computer where I have this particular file called descriptives, and I'll try to make use of it as in the form of a regular package. So I'm going to show this is very, very important for work Python. Yeah, descriptives. Here I have my file descriptives. So what we need to do, we try to make a folder. We call it as scripts, and in this scripts I transfer this file. I think I need to go to the editor, save as, and this time I can go to the work Python scripts descriptives, and after this what I do is go back, create another text document, and call it as __init __.py. That's it, nothing else. You need not do anything, just open, and you need not even open and save that, but it's a matter of precaution. That's all. So we don't need to do anything. Now what we try to do, we'll go back and copy the properties of this file. I think this is the path of the copy. Then please remember the name of the directory or whatever it is. And now what I do, I open the you can also open the editor, but okay, we'll go for the editor. Open the editor. Now I'm not going to run or execute from this script file. I'll go to the directory. For that I need to import a module called OS. I'll check my present working directory, current working directory, and this is the current working directory. What I do, I'll change the directory, OS change directory. Then you should remember scripts, and then close. I think we have scripts. Yeah, scripts. Yeah, OS get current working directory, Now you should be able to see. Now you can go for the import descriptives as desc. Yeah, if Python is silent, then it started recognizing your I think I closed my directory. So now Python recognized your module descriptives as one of the valid modules. Now you can go for the desk my mean, and you should be able to see that or you just come to this level, press tab 2 times, then you'll have all the methods. I mean, the IntelliSense in Python starts and it will try to show you all the methods, and you can choose any one of the method, my mean, range 1,5. Yeah, same we can also go for the skewness and press tab. It will recognize desk, kurtosis, and I mean, I think it is better to go to the previous command, and yeah, that's all. Now we'll go for the Jarque-Bera test. Jarque-Bera test and range 1,5. Yes, so this is actually the p-value for the. This is how we can write the source code to test the normality of the underlying or the studied data sets in Python. This is very, very important for people who are engaging in the data analytics, especially if their job is to study the sample distributions and their properties. And in this video I've shown you how to test the sample distribution, whether it is normally distributed or not, by using Jarque-Bera test, whatever it is. So if you like my video, please press like. Kindly don't press unlike or dislike, and subscribe to my video channel. Stay tuned for the new content. Thanks a lot for watching my video.